No, absolutely.
Okay.
Oh, I see. All right. Okay, good morning everyone, and welcome to Michigan, to the Lineweaver Institute for Theoretical Physics. The workshop is going to start, but the first, I want to introduce my colleague and the senior science advisor to the Lineweaver Foundation, who's going to say a few words to get us started. James Wells.
Thanks, Leo. Welcome to Ann Arbor and the University of Michigan. I believe this is the first public event after the Lineweaver Foundation has made very substantial gifts to theoretical physics across the country. We are one of 8 institutions that are part of the Lineweaver Institutes and Forum Network. The Lineweaver Foundation has invested, I think it's over $150 million in theoretical physics in our area. And the foundation, Larry Lineweaver, who's the head of the foundation, who founded the foundation, believes that theoretical physics is the point of the spear of long-term scientific progress. And University of Michigan was the first institute that the foundation funded approximately a decade ago. And things have gone well for us here. And we have been outward facing with the community, with theoretical physics across the country and across the world. Workshops like this have been part of that outward facing aspect of the University of Michigan's Lineweaver Center for Theoretical Physics. That's what we were for about 8 years. Last year, the foundation added 7 more and made a network of institutes. And those include Caltech, Berkeley, Stanford, Chicago, Michigan, Institute for Advanced Study, MIT, and Harvard. And the hope is that this will greatly benefit the community, not just those 8 institutions. This workshop is one of those attempts to help benefit the community. But you'll see a lot of postdoc hiring, student fellowships, and conferences and workshops across the country associated with the Lineweaver Foundation and Lineweaver Institutes. So this workshop, I think, is a really great workshop to kick off the big network of workshops. Black hole physics is such a extraordinary topic. You're all here because you understand that and recognize it. Theoretical physics thrives on problems and conceptual difficulties, and black hole physics just eats conceptual difficulties for lunch, for breakfast every day. And you're going to tell us all about the amazing things in black hole physics. So thank you very much for coming, and thank you, Leo, for giving me a few minutes to share what this foundation is doing. And I hope you have a really nice conference and workshop and enjoy your visit to Ann Arbor. Thanks.
All right, so thank you, James, very much. So we are going to now start with talks. Before, I'll give you a few instructions. Again, this is going to be, I'm going to repeat, but the key thing, if you have a question, talk to one of the organizers. Talk to me. Beneath is the person who knows everything. Jim and Finn can help you, or any local students. So that's your source, okay? So here I want to emphasize that the spirit of the workshop is to really try to discuss and get into discussions of problems, not just a presentation of what you have done. So we have asked the presenters, of the speakers, to try to finish the last 15 minutes of your hour-and-a-half talk is to actual discussion. So you should put some slides about open problems and we want to have that kind of interaction. You are supposed to have picked a name tag outside, so if you haven't done so, do it. If your name tag is not there because of some issue, just make one name tag. That will help us interact. Coffee breaks are scheduled, so for all the most up-to-date information, go to the website. But we have a coffee break in the morning, coffee break in the afternoon, and lunch is self-organized. So you can, again, you have a list in the website, but you can ask students, or you can follow anyone local to a place that you will find good food. So if you have any pressing question, this is your 10 seconds to ask. If not, I am happy to introduce Christoph, who's going to start up the conference for us. So.
All right. Thank you very much. Mike.
What mics? Do we have mics?
Yeah.
All questions. Everybody thinks they can speak louder.
No, yeah. It's important to use the mic. We are not broadcasting the conference, but we are recording it, and it will be available. So I think this is useful, and it's important to use the mic, otherwise it will not be caught up. So if you have a question, we will try to get the microphone to you, all right?
Okay, can you hear me okay then? The room's so we have been upstairs.
No.
Closer to you. Okay, like so.
We can only hear if you say something.
Is there a
Well,
green,
okay, let me,
green light on? Is that on?
Yeah, it is on.
Somewhere further up. Hello. People can hear me now? Okay, let me just get this connected somewhere where I won't turn it off accidentally. Good. Okay, so I can hear that this seems to be working. Let me know if it goes out or I move things. Let me start, of course, by thanking our organizers, thanking Leo and Vinith for this nice workshop and for the invitation to actually be part of it. It's a great pleasure to be here. And what I want to talk about is a certain class of solutions in complex type 2B supergravity or string theory and their relation to the IKKT model. Among the main themes that were advertised, connected with the workshop, this probably most directly connects to emergent geometries, emergent space-time, and that line of thought. But it will have complex solutions in there, which of course are relevant all over the place in black hole physics. So maybe this will be a little more broadly amusing as well. And it is slightly amusing for a different reason, in that it indirectly connects me back to some work, some line of research I was working on when I was here as a postdoc. So anyway, let's go ahead. The title is a little bit of a proliferation of acronyms, which for many of you are very familiar, but I don't want to assume that everyone is. So we're going to start things at the beginning and unpack this a little bit more step by step. But before jumping into this, for those who want to tune out somewhere halfway along the talk, I'll give you the main punchline and technical result that this is based on without any fuss. We have a classification of complex supersymmetric solutions realizing the superalgebra F4, complexified, in type 2B string theory, complexified, and an exhaustive discussion of all their real forms in the various real forms, standard string theory, theories like type 2B star, type 2B prime. We'll explain what these are in a little more detail, but as a summary of the results, this is it. And I should say that this is based on work with Eric Doker and Michael Goodperle. And in the talk, I will also have some, in the spirit of the workshop, some comments on ongoing work where things aren't quite as settled yet. But okay, very good. Let's start at the beginning. The IKKT model is a very simple model. It's in some sense, somewhat more enigmatic sibling of the BFSS model. It's simpler, and that sometimes makes it harder to understand. It's a matrix integral. We have 10 matrices x mu, n by n, which together form a vector of an SO10 or SO1,9 global symmetry. And we have another set of matrices psi alpha, which form a spinor representation of an SO10 symmetry. And that's it. an integral over matrices. It arises as the reduction of 4D n equals 4 super Yang-Mills to 0 dimensions. Can also be seen as 10D n equals 1 super Yang-Mills reduced to 0 dimensions. The point is all space-time is gone. It's a simple matrix integral, and it connects in type 2b to the physics of d instantons, where the solution corresponding to d instantons somewhat reflects the simplicity of the model. It's very simple. We have a flat 10D geometry. It's Euclidean. There's a relation between the axion and the string coupling, the dilaton, which are both given by very simple expressions. In some sense, there's not much to this solution. Why is it interesting to study, or why do we care? If there were some kind of gravitational description, some holographic dual description for this model, it would have to be something fully emergent. Unlike standard ADS CFT, where we start out from a CFT, which already knows about time and has some underlying space-time, and then we grow extra dimensions from that, here there's no such thing as space-time in the model. Everything that comes out in terms of a gravitational description has to, in some sense, be emergent. Somewhat more ambitiously, it has been hoped that this model would provide some non-perturbative definition of type 2b string theory, somewhat in the spirit of BFSS. But I won't have much to say on that. I'll focus on the idea of gravitational descriptions for this matrix model. OK, so what makes this interesting in terms of dual descriptions is also what makes it challenging. The fact that this model doesn't have time, there's no energy scale, there's no RG flow, none of the things that usually help us, ADS CFT, iron out what the dual is, are present here, and so it's much less clear how to find dual descriptions. On top of that, the integral itself doesn't behave nicely with n. If I dial the size of the matrices, it doesn't depend smoothly on this parameter, and so it's not a nice observable actually in the usual sense of large n physics, and it's not clear how to describe what to connect this to. Somewhat relatedly, the simple d-instanton solution does not have a decoupling limit in the usual in the usual sense of d-brane solutions. It's just flat space. It's really hard to understand how to make this work. So very interesting, but also very challenging. And nicely enough, then, to note that about a year and a half ago, there was actual progress on finding gravitational descriptions for this model. And they are based on deforming the model in a way which connects it to higher dimensional branes, which we tend to understand a little better. So the idea is we take these 10 matrices, we split them into two groups, a triplet, and then all the rest. We give different masses to these two, different mass terms for these two groups of matrices, and include for the triplet a cubic interaction term. All of these have precisely engineered relative coefficients, where the idea, of course, is that this deformation preserves some supersymmetry. 16 supersymmetries, that is. And combined with the bosonic symmetry that this splitting of the matrices preserves, which leaves an SO7 and an SO3, this points to a particular superalgebra, which is F4. So that is the F4 in the title, and gets us going along the direction I want to talk about. This deformed model has non-trivial saddle points, where the triplet of matrices that we singled out are given by SU2 generators. So these TAs are satisfying the SU2 Lie algebra, and the X's are a rescaled version of these generators. So any choice of SU2 representation, some combination of irreducibles, gives us a saddle point for this matrix model. And this is the target for holographic descriptions. These saddle points arising in this polarized IKKT model. In string theory lingo, the idea is that this cubic interaction term in the model allows the d-instantons, which themselves have no world volume, nothing of the type, it allows them to polarize by the Myers effect into spherical d-strings. So they puff up and produce d-strings for us. And based on this intuition, two proposals have been made for gravitational description of these saddle points in type 2b. The first one is based on modeling this polarization deformation as turning on a certain flux in the string theory background, NS flux, and then models the saddle points that we are having in this model as probe D1 branes in this background, whereas the second proposal is based on fully back-reacted solutions, which carry D string and 5 brane charges. So these are the two proposals, and we're going to take a look at them one by one. Okay. So the first proposal, as I mentioned, starts out from the D instanton solution was flat space, and we'll just write this in a form which makes the symmetries manifest that the deformation preserves. So we have an S2 realizing SO3, we have an S6 realizing SO7. This is just flat space. We turn on H3 along the first 3 directions, and it turns out that this can indeed be completed to a solution of type 2B string theory, where the axion and string coupling still satisfy the same relation as in the D instanton solution, but the profile is changed. It's not quite a nice and regular solution. As you can see from these expressions, the string coupling goes negative if you make R or little r large. That means the string frame metric collapses and the solution is singular. But you can hope that if you stay sufficiently far away from the region where this happens, you stay deep inside, then maybe things are okay. You have to just go with it for a little bit. You also see that the relative coefficients here break the symmetry, reflect the symmetry breaking, and this is the background into which then D1 branes are basically dumped. Okay, so the proposal is that the saddles of the polarized IKKT model correspond to configurations of D1 branes, which wrap this 2-sphere and otherwise are sitting on the vertical line in this little cartoon. They sit on the vertical line because that's where the S6 collapses, and so they can preserve the symmetry. Okay, the idea is then that these D strings carry world sheet Maxwell field, and the flux associated with this Maxwell field encodes the instanton charge, representing what initially was the instantons, then puffing up into a D1. In turn, this parameter basically tells you where exactly along this vertical line the D1 branes sit, and allows you to calculate the on-shell action of these D branes. And as a check for this proposal, one can first of all match the parameters between the two descriptions, and then connect the D1 brane action to the polarized IKKT model action. So some nice and encouraging results here. That's the first proposal due to Hocknell and Liu. The second proposal I want to also briefly discuss is based not on probe D1 branes, but on fully back-reacted solutions, which have, of course, the same symmetries, SO7 and SO3. The geometry is more complicated. We have S2 and S6 as they were, but now these are fibered over some 2-dimensional space, where the 2-dimensional space is the upper right quadrant, and at each point we have an S2 and S6 attached in ways such that their sizes vary. The solutions are described indirectly in terms of an electrostatics potential. So the idea is you're solving for some electrostatics potential V, which is defined by putting some charged disks into the upper quadrant. You solve for this electrostatics potential, you feed this into particular expressions for the metric functions and so forth, and that gives you a back-reacted solution. Okay, so how do the parameters work? In the geometry here, the color coding tells you which of the spheres collapses. So on the vertical line, you have the 6-sphere collapsing. On the blue disk, you have the 2 spheres collapsing. And that means each of these charged disks introduces cycles. By fibering S6 over a curve like so, you create a 7 cycle, and that carries brane charges. So each of these disks introduces a set of charges and is supposed to represent one group of SU2 representations of the same dimension. So for each disk, there is a D string charge and NS5 charge, giving you the multiplicity and dimension of the corresponding representations in the polarized IKKT model. Okay, so this is the saddle. This is the proposal here. These solutions are still asymptotically flat. Not quite flat, but asymptotically. If you go far away from these disks, the geometry becomes flat. The string
just maybe, so is the solution supposed to, the matrix model describing fluctuations about this, or is it describing these class of solutions? What is it describing?
Yeah, so the proposal is that every one of these solutions, defined by a set of these charge disks, corresponds to one saddle point in the polarized IKKT model. Now, if you're doing ADS-CFT, we have a very good understanding of what happens then. You fluctuate both sides. We have a precise dictionary telling you how things map on the two sides. But here we're not in the regime of standard ADS-CFT. So this is a bit unexplored territory in that sense, I would say. So having a complete dictionary of how you relate fluctuations on top of these saddle points is something which would be nice to understand.
Like in principle, this is something that's computable, that you could just do fluctuations of the matrix model and plug it out.
In principle, you can sort of, even before computing, you can classify what fluctuations are there, what symmetries do they preserve, how do I want to match this on the gravity side. That would be nice to have. We're not quite there yet. And actually, there are some puzzles here, which I'll get to in a moment. But the idea is it would be nice to establish sort of the baseline. Okay, so we're being a little more, we're a little less ambitious here. Okay. Well, I should say these authors.
So about asymptotic, why is it flat but not like something more like plane wave? If I compare to BMN.
Yeah. So right. So basically, what you have is the asymptotics of the instanton solution, and that just came with flat space. Yeah. There are many analogies and parallels with BMN. But here we're doing not the zero branes, but the instantons.
I think this can be understood as competitive by the BMN by on SY bar. But for the BMN, the same configuration, if you go to asymptotic, you get the plane wave. Mm-hmm. So that's why I got confused why, in this case, asymptotic, you actually get flat, but not something like plane wave.
Yeah, let me, so I would, morally speaking, there's, of course, some idea of dimensional reduction. But these solutions, I think, are slightly different. OK, good. So we have some asymptotic region where it becomes flat. In these solutions, the string coupling stays positive. So that's nice, sounds much better. But as a trade-off, the axion just keeps going. It diverges as you go far out. So in some sense, both of these have a little bit of an issue out there, but that's what it is. In contrast to the previous proposal, there's no B2, no H3 flux turned on. Instead, these solutions have asymptotically Raman fields turned on. The two form, and that is supposed to encode the deformation in these solutions. So that's the general construction, and you can infer many things from just knowing what the solutions are indirectly through this electrostatics potential. But sometimes it's also good to have explicit solutions, and the explicit solutions were given for a limiting case where you have a single disk which is sort of far off this grounded plate down at the bottom here. Okay, and that corresponds, according to this dictionary in IKKT, to a small number of large dimensional representations describing the saddle point. The checks for this proposal are based on mapping the equations describing this electrostatics problem to the saddle point equations in the IKKT model. You can't quite compute the action very easily because you have this asymptotic region, the solutions are non-compact, and formally the action is infinite. So that is a little harder to do here, but there are some checks and matches nevertheless. Okay, good. So that's a quick rundown of these models. What we have then is two very appealing or intriguing proposals, I would say, which almost appear compatible. That was explained nicely by the authors of the second proposal. Both of them want to model fuzzy spheres as D-strings. The fuzzy sphere saddle points with the SU2 representations in the polarized IKKT model are modeled as D-strings. But they disagree on which two-form implements the polarization deformation, and they disagree on the asymptotics. Now, it turns out the asymptotics and the two forms are actually S-dual to each other. So they are not that different after all. But from that perspective, then it's puzzling that they both use D-strings. If I were to do S-duality, D-string should become a fundamental string. And I don't usually get to do S-duality just to a few ingredients in the construction. You do it everywhere or not at all. So they're not quite compatible. That's what it is. And we're in one of those situations where two roads diverge in the woods, and you can go with Robert Frost and sort of meditate over this, or you take a good bit of baseball wisdom, Yogi Berra, if you come to a fork in life, just take it. And that's the approach I want to take here. And what I take this to mean is that both of these proposals are intriguing. They get some things right. Whatever the relation between them, they seem to be convincing enough to say that there is something there. And so we can go with it and try to improve on the situation, understand things better than we do now.
So, Christoph, I got confused about what you mean by a proposal. So you have a matrix model, the IKKT model. I believe you took a massive deformation of it. Then you take a certain large n Toft-like limit that I think you didn't discuss in great detail, but fine. That means you have defined a certain quantum model, and it has many vectora, right? Is that right? So in principle,
well, we didn't get quite so far as in the IKKT model. What exactly did you mean? It's a certain massive deformation or whatever, it has many vectora.
Right.
Now you have then gone straight to what is the gravity dual of this? So proposals, they need two sides. Are each of these supposed to be dual to the same part of the IKKT model? Is it the same vacuum in the IKKT model? Whatever. Yeah. So I mean, can they both be true? Because is the IKKT model here, I believe, is a family. There's a whole bunch of vectora of this Lagrangian.
There is, so this is just a matrix integral, right? So some of the things which were usually used to aren't quite there. But the idea is that each of these that in this case you have a map between saddle points of the polarized IKKT model and gravitational configurations. You look at Euclidean solutions. Clearly, okay. In this case, it may be small.
So there are many saddle points, and they can have many gravitational duals, yes?
Yes. And they both have a map between the parameters characterizing the saddle point. One saddle point means a set of SU2 representations. I start with a reducible representation, I decompose it into all its irreps, and then I have a set of parameters. How many? What are the dimensions, and how many of each? That's the data. And this data is reflected in the gravitational descriptions. In one proposal, it corresponds to a configuration of charge disks, where their heights and charges correspond to the parameters characterizing IKKT saddles. And in the other case, it's probe D1s carrying different d-instanton charges. So they describe the same thing, or they're supposed to describe the same thing, as far as my understanding goes. And that means you should be able to compare them. Does that... So it's really, each saddle point is supposed to correspond to one configuration in the gravity description. Good. So anyway, they use different ingredients to make proposals here. And again, there's some room for maneuver because we're not in the realm of usual ADS-CFT where you start with a brane construction, you take a decoupling limit, you get your gravity dual, and then that's that. Here, there's not quite such a thing. And so there's a little bit of room for wiggling and maneuver. Nonetheless, as I was trying to say, whatever the relation between these proposals, I would say the checks that have been provided tell us that there's something interesting there. And it would be nice to understand better what actually, these two proposals are there, and we can go ahead and try to move forward. Two things come to mind, which would be nice for moving forward. The first one is that both of these proposals are beyond standard ADS-CFT and rely heavily on symmetries. So it would be good to rigorously and fully understand the playground. That is to say, what are the candidate solutions with F4 symmetry that could potentially match to the saddle points of these matrix integrals? That's point number one. We want to chart systematically and completely the space of candidate solutions. Excuse me. The second point is that Euclidean theories tend to be complex, especially when combined with supersymmetry. And the same is true in the IKKT model. The Euclidean version, which is used in these constructions, has complex supersymmetries. There's actually no real form of the F4 superalgebra with SO7 and SO3 symmetry. So this should really be understood as some complex contour integral. And as such, you can ask, what are all the possible contours one could potentially look at? What is the structure of this in the fully complexified setting? And that makes, motivates the idea to sort of fully classify complex solutions with F4 symmetry, to have a grasp of what the playground is, understand all their potential real forms as they may exist, and then line this up with the IKKT integral in a complexified setting. So that is basically the motivation for what I'm going to tell you. And before going into the main part and actually telling you about the results, I want to sort of add one additional perspective, which connects back to things I've worked on in the past while I was here. And that has to do with 5D CFTs. So completely different cup of tea on the face of it. 5-dimensional conformal field theories have been constructed in large numbers. And the superconformal algebra in 5D also happens to be F4. And the point here is that these solutions, these back-reacted solutions which I was showing, are actually were constructed from duals for 5D CFTs by some form of analytic continuation. Okay? So the idea is, in type 2B, there are large families of 5D CFTs, and the holographic duals for these take a closely related form, where I don't have S6 but ADS6 and an S2, and they're warped over some 2D surface, so much like the quadrant. There are infinite families of such CFTs and supergravity solutions, and basically the S6 cross S2 solutions that I was mentioning with the charge in connection with the charged disks are constructed by taking these ADS6 cross S2 solutions, sprinkling in some factors of I and phases in clever ways in various stages of the expressions, and then continuing ADS6 to S6. That's something you can do, and has been done in a way which made the authors of this proposal argue that the result satisfies the Euclidean equations of motion. So that's a clever way to get general local form of these solutions. That's where this expression in terms of a potential comes from. And then the global analysis, like what are regular solutions, is completely different in this Euclidean setting compared to the ADS6 solutions. But it is one step which featured in these constructions. It strictly speaking leaves an open end in that these solutions were constructed to satisfy the Euclidean equations of motion. And the question of supersymmetry remained basically open at this point. It's natural to think that there probably may be, but it wasn't strictly shown. So that's one further motivation to tie up this loose end if there are questions regarding the proposals, and provide properly or manifestly supersymmetric constructions. And then there is additional motivation from the 5D CFT side for studying complex solutions with F4 symmetry, which I might get back to a little later. For now, I want to just stick with IKKT. Okay, so that's the motivation. And now with that said, for the main part, I will have 3 parts. First part, I want to introduce this setting, complexified type 2B supergravity. What we mean by that, discuss all its real forms of theories in that sense. And then the second part, we'll talk about summarizing kind of the results on general solutions with complexified F4 symmetry and their real forms. And then in the last part, we're going to circle back on IKKT and give some new perspectives on these solutions with the multiple charge disks. Okay. No questions? Then I will just start with the main part. Good. So complex type 2B. What is the idea? Type 2B supergravity is a theory which can be formulated in a way which does not use any complex conjugation. we're using a real formulation where we're working with Majorana-Weil spinors, and that means the whole bosonic and fermionic field content. We can write the action for it, the supersymmetry transformations, all these little ingredients without ever using complex conjugation, by just using the Majorana conditions. That makes it natural then to start from that formulation and complexify the theory in every way possible, basically. We start by complexifying the underlying spacetime coordinates. We complexify the metric, or the bosonic fields, drop the Majorana condition for the spinors, the gravitinos, the dilatinos, and the supersymmetry transformation parameters to get a theory where the fields have, by construction, holomorphic dependence on the coordinates. The action and SUSY transformation are holomorphic in the fields. So everyone is holomorphic in every way. We formally have 32 complex supersymmetries now, and they give us complexified BPS equations, which is really the kind of thing we're trying to solve. I'm not going to spell any of this out in detail, but I want to mention it here because this is sort of what the eventual results are based on. In this process of complexification, we also enhance the usual SL2R duality symmetry of type 2B to an SL2C. Okay, so this is basically what I mean by complexified supergravity. It mirrors basically a complexification one can do in the IKKT model. By construction, it contains the standard notion of type 2B supergravity as one real slice, but that's not the only real slice that there is. Okay? You can basically, once the theory is complexified, I can ask for what are all the possible restrictions to real forms, and that has been done some years ago by these authors, and we will follow their basically discussion. The idea is we're going to insist on having a real metric. A real metric gets a signature. We're going to ask for t time lag directions and then 10 minus t space lag directions. We are also going to insist on real string coupling and some form of a reality conditions for the spinors where the charge conjugation matrix depends on the signature, and then there can be a twist in the reality conditions. We'll allow for that. And once you have this set up, it's a matter of going through all the other fields and looking at all possible ways to impose reality conditions on the remaining fields so that you get a real action, compatibility with supersymmetry, so on and so forth. And this turns out to give a nice set of real forms, which is not all that short a list. There are 4 families, basically. The first one is type 2B sub R, which is standard type 2B supergravity as we know it and like it. It comes with 2 friends who have funny signatures, 5 time lag directions and 9 time lag directions. And in this family, all the bosonic fields are real, and we have a standard Majorana condition. They're then accompanied by 2 more families, which have the same types of signatures, 1 time lag, 5 time lag, 9 time lag, but have twisted reality conditions. In type 2B star, all the Ramon-Ramon fields of type 2B are imaginary, while the NSNS2 form is real, and the spinor reality condition is twisted in a particular way. Type 2B prime is closely related, has actually just the role of the 2 forms exchanged. B2 and C2 change their reality properties. And then there is a final family which only comes in exotic signatures, 3,7 and 7,3. And those, the 2 forms are imaginary and everybody else is real. So this is sort of an exhaustive list of all the real forms of type 2B supergravity that we can look at. And this will inform what to do with in terms of real forms of F4 solutions. This was a construction basically based in a sort of bootstrappy way in supergravity. We just complexified the theory and looked at possible real forms. But these theories actually have an origin in string theory, where they were first identified and constructed by Christoph. The idea is we have this nice kind of schematic representation of all the real forms. This is taken from a later paper. And in this schematic, we have type 2B and type 2A, they're the standard versions. They get a plus plus superscript, or related by T-duality, and we have S-duality here. And the idea then is that if we do time-like T-duality on type 2A, that gets us to some type 2B theory. But now the D-branes are all Euclidean, and that means the Ramon-Ramon fields are imaginary. So this is the theory that I called type 2B star on the previous slide. particular, this theory has Lorentzian strings and Euclidean D strings. And if I do S-duality on it, I'm not going to go back to the theory itself, because they differ in their nature. And so what I get by doing S-duality is a new theory, which happens to be this type 2b prime theory on the previous slides. And you get the idea. One can go through chains of dualities here to really fill out this whole graphics. I don't want to go through this in completion, but the point is that all the real forms I listed somehow have an avatar and are realized in string theory. This puffs up basically the figure even more. This is now with all the signatures indicated. You see that on the right-hand side, where strings are Euclidean, the signatures change by duality transformations. On the left-hand side, they're preserved. So that's the kind of theory space that I'm looking at when wanting to discuss real forms of F4 solutions. Very good. In terms of connecting this into ADS-CFT, these real forms were connected to supergroup gauge theories, where I take as a gauge group, not a regular SUN group, let's say, but some supergroups, and that connects to negative branes, and in these constructions, these exotic real forms of type 2b all made appearances. Okay, so that's basically the setup, and now I want to talk a little bit about F4 solutions. What's the idea? Well, the idea is to fully classify these F4 solutions, not in one particular real form, but in this fully complexified setting of type 2b supergravity that I introduced.
Can I ask a question?
Yes.
You said that you have different theories. Are there different theories or different complex solutions of the same theory? How do you know?
Well,
I guess I was thinking if you take imaginary, well, let's say just matter fields, they might have a preferred reality condition where the integrals converge.
Yeah.
This could be complex solutions of that theory, but is it a different theory?
Yeah. Okay. So when you're talking about duality relations, of course, what is a different theory really is a little murky anyway. So in some sense, these are defined as, so you're looking at a theory as defined by a set of reality conditions, and then whether you see it as a complex solution in the original theory or a real solution in the complexified theory, I'm not sure where you would actually draw the difference here.
But let's say from the point of view of the convergence of the path integral, just for matter fields.
Yes.
Just to avoid questions about gravity, then there could be a preferred choice that will make them well defined, right?
Yeah, this I think is a good question. Like generally speaking, how to make sense of these theories. I would see issues even before that, like what is a theory with 5 time directions? What is a reasonable time evolution in this setting? So there are certainly many questions you can ask here. The idea for this cataloging of these real forms was to take seriously T-duality and along the time direction. So I'm not making a claim here as to how independently well-defined these theories are. They emerge from the standard type 2b theory by chains of dualities, and one way to make sense of them is to basically transport everything along duality chains. Could be something you might have in mind, but there's no claim here.
But you could also say that there are complex solutions of the original.
Yeah, if you fully complexify the theory to begin with, then they're all different real slices. So if I think in terms of good. Okay, so that's the playground in some way. And now the idea is the d-instanton solutions inherently live in Euclidean settings and should be understood in a complexified setting. And so we're going to generally construct F4 solutions which live in this complexified theory. And then afterwards, I can ask which real slice may I take and what kind of real slice, real solutions do I find in there. But the starting point is very much to say complexified theory, and that's it. So if we take the complexified superalgebra F4, we have bosonic symmetry, SO7 and SO3 over the complex numbers. And that basically dictates the ansatz for us for the solutions. We need complex symmetric spaces to realize these symmetries. And if I sort of look ahead and think in terms of real slices, then any such complex space will contain de Sitter space and anti-de Sitter spaces of any signature where the sum sums up to the dimension of the complex space as different real slices. So this really is kind of a classification tool to put these spaces in there. And then the full geometry for our construction should have a 6-dimensional complex symmetric space, 2-dimensional symmetric space. And then these can be, excuse me, these can be warped and fibered over some complexified 2-dimensional surface, which I'm going to call sigma sub c. So by a very similar argument to the usual Riemann surface discussions, we have a complexified surface here, so 2 independent complex coordinates. We can take the metric nonetheless to take this usual conformal gauge type of form. And then for the surface, we can have real slices and complex slices, depending on what identification we impose on these 2 complex coordinates. So that's basically the discussion here. And with this ansatz, we can then go into the BPS equations and solve them. And that's a major tour de force. Leads to PDEs on this Riemann surface, which need to be disentangled, decoupled, and integrated. And I'm going to tell you nothing about it because it's really technical. But the result is quite nice. We get the general solution to the complexified BPS equations, parameterized by a set of 4 complex functions on this Riemann surface. These complex functions basically appear as integration constants, and they satisfy something akin to holomorphicity conditions, where each of them is independent of one of the complex coordinates. And then any choice of these 4 functions gives you a solution in complexified type 2B supergravity in a way which I will only give schematically. We have sort of some composite quantity, curly G, which is built out of A1 and 2 and A1, 2 tilde. The metric can be expressed entirely in terms of this composite quantity, while all the other supergravity fields that are allowed to be turned on directly depend on these complex functions. And the reason for this is that this is the Einstein frame metric. It's SL2 invariant, supposedly, and so it only depends on a particular SL2 invariant combination, whereas the other fields transform non-trivially. In fact, the entire SL2C transformations of type 2B are induced by very simple transformations of these complex functions, and that is quite useful for the constructions as one goes along. So it's good to have this full set of data. Okay, so this is the setting where, generally speaking, we expect Euclidean solutions to live. We have this double set of data compared to previous constructions and precise relations between the composite quantities and this data. So in terms of an analytic continuation, you don't get to sprinkle in signs just anywhere, and not anything goes. And we can now, go ahead and look at the real forms as we set out to do. Okay, so what does it mean to restrict to real forms? That needs a certain set of input data. It needs, first of all, a choice among these families of type 2B real forms, meaning a set of reality conditions, a choice of overall signature, T time-like directions, and then we have some more detailed data where these symmetric spaces M6, M2 have to be given curvatures, and we have to distribute the total number of time directions over these 3 constituent spaces. So overall, we get some 6-dimensional symmetric space, P time-like directions, 2-dimensional symmetric space with Q time-like directions, and then possibly sum of sigma on sigma 2. These choices feed into the reduced BPS conditions and the charge conjugation matrices, so they very much affect whether consistent solutions can be found or not. And a classification then means identifying all choices of this data which are compatible with the reduced BPS conditions. So some way where the reality conditions act as symmetries on the BPS conditions, and that then in turn leads to relations between these 4 holomorphic 4 complex functions and the 2 complex coordinates on sigma. So that's the program. Again, going through it is technical, but can be done, and we get some results here. So I'll jump straight into that. This is a table of all the possible real forms, where the signatures are either 1,9 or 3,7. There are similar tables for the other signature choices, but this is it. We see a few things. First of all, in standard type 2B, there are only two cases. And those are cases which have been discussed before. So there's nothing new here. We basically get the aforementioned duals of 5 DCFTs and then a set of ADS2 solutions which connect, which have been discussed before as well. But then as we go along, we get more real forms in type 2B star and 2B prime, and some in type 2B3. We see that the symmetric spaces can have all sorts of signatures. In standard type 2B, there are always one negative curvature, one positive curvature. Here, this is not the case anymore. For each of these solutions, each of these entries in this table corresponds to precise relations between the complex functions we introduced, and the analysis of global solutions is going to be totally different. So much like the IKKT solutions differ from 5D CFT solutions, one could basically go through each and every entry here and have a long discussion, which I don't want to do. But it would be interesting to sort out which of these solutions actually connect in some way to IKKT, which connect to 5D CFTs and maybe supergroup versions of them, supergroup gauge theory versions, and which may connect to something else altogether. It's a big playground to explore. And in the last part of the talk, I want to zero in on one of these real forms and actually bring this a bit back to the IKKT duals, give a few, hopefully, eventually useful perspectives on these solutions. Good. I should also say before moving on that there's a non-trivial consistency check where the bosonic algebras which arise in real forms have to, of course, line up with real forms of the complex superalgebra F4, and they do. They all fall into the list of real forms, and it's actually exhausted. So supergravity could reproduce this old classification of real forms here, which goes back to NAM. And notably, there's no S6 cross S2 cross sigma real forms, so these are genuinely complex solutions. OK, good. So let's look at DS6 S2 sigma and its connection to the Euclidean solutions that connect to the IKKT model. The reason for looking at this particular real form is that it has a direct path to S6, S2 warped over a Riemann surface. Both of these spaces have positive curvature already. So the analytic continuation from de Sitter 6 to S6 is trivial. In the solutions, moreover, nothing depends on the volume form of the 6-dimensional space. So this is a much easier path than what has been done before, going through ADS6 solutions and sprinkling in phases. For this particular real form with de Sitter 6, the relations between these four complex functions are in such a way that the tilted ones are related to complex conjugates of the untilted ones. There's some minus and some plus. Having these different signs is what makes some of the supergravity fields imaginary in line with type 2B star. So we indeed get imaginary Raman-Raman fields. And we only have one complex coordinate left on the Riemann surface. One could now trade one of these remaining holomorphic functions, eliminated by a choice of coordinates, and that would connect to the electrostatics potential formulation that I mentioned initially. Doing away with one of them leaves one holomorphic function, can be traded for one harmonic function, and that's an electrostatics potential. But that's a bit of an unfortunate thing to do. It sacrifices SL2R covariance, and the redundancy of having two holomorphic functions around is actually useful for constructing explicit solutions. So we're going to keep them. We're not going to end on an electrostatics formulation, but instead on a formulation with two holomorphic functions in the game. And that way, we only need to specify the topology of sigma as input. And then we can go ahead. It's not quite clear to me where this electrostatics problem with the charged disks, you can wonder where it fits in the space of solutions. Are these all the solutions there are? Are there different ingredients which you can add? It connects nicely to analogies with BMN duals, but is it really all there is? And so we're going to avoid making any commitments here and just classify what you can do. Okay, so let me lay this out a little bit. So the idea for finding globally regular solutions of this particular geometry is we start out taking sigma as some Riemann surface with boundary. That's the first input data. And then we're going to have to ensure that we get real and positive metric functions in the actual solutions so that we get a real metric as desired. We want positive string coupling in the interior of sigma everywhere. And we want boundary conditions on the boundary of the Riemann surface so that either M6 or M2 collapse so that we get a closed off geometry without sporing the boundaries in the discussion. And this is what you need to go through and solve. And again, is something which I'm going to cut short a little bit. But I want to give sort of the gist of it. Metric positivity is something which can be solved exhaustively. It leads to yet another electrostatics problem, but a very simple one. All you need to do is this particular combination of the differentials of these holomorphic functions needs to be an electrostatics potential which is positive in the interior of sigma, negative, and vanishes on the boundary. So we know how to solve something like that. We put a bunch of charges in there, a bunch of mirror charges in the complement of the Riemann surface. And this gives you an exhaustive solution for this particular combination of these holomorphic functions. Okay, so then there are some further ingredients. We need to implement the boundary conditions that M6 and M2 vanish somewhere on the boundary of sigma. That is basically leads to a symmetry relation between the two remaining holomorphic functions. And then we can allow for additional isolated singularities with the idea to introduce brane sources and things like that. Bottom line is, one gets a very explicit expression for these differentials, which completely specifies the problem. There are these S, A plus minus, or the charges in this auxiliary electrostatics problem. And we have a bunch of singularities on the lower, in the denominator here, which allow us to realize basically different geometries for this Riemann surface. We have the 1 over square root singularities. They turn out to correspond to basically corners. You can do away with them locally by a coordinate transformation. And so they correspond to corners in the geometry. We have the 1 over 5/2 singularities. They correspond to asymptotic instanton solutions. Geometry becomes flat, and you get the instanton asymptotics. And then we, in addition, can have poles where degree 2 or degree 3 poles on these differentials. They can be, the degree 2 poles are allowed when the S2 collapses, degree 3 when the S6 collapses. Bottom line is to introduce PQ5 brane charges and PQ string charges into these solutions. So there are some additional ingredients besides corners and asymptotic regions which one can play with here. Okay, and one advantage of this construction is these are fully explicit differentials. Anything else I need, I can get from holomorphic integrals. The functions themselves, any of the composite quantities, are very straightforward to construct from this, and so we can get explicit solutions which will allow us to do some detailed checks, hopefully allow us to do some detailed checks and analysis of these dualities. Okay, let's see how this fits with the previous constructions. The minimal thing you can do is take one square root singularity and one with exponent 5/2. That gives you one corner and one asymptotic region. And this is precisely the cavity that we discussed in one of these proposals. It comes here out as the simplest choice you can possibly make. The one difference being that you have, well, the full SL2R orbit right away. But otherwise, this is just a way to kind of anchor the constructions. The next thing you can do is recover the full set of these charged disk configurations. What do I want for these charged disk configurations? They correspond to sequences of boundary segments where alternatingly S6 and S2 collapse. So we just put a bunch of square root singularities in the denominator and a set of charges in the numerator so that we get the right asymptotic behavior. It's very explicit. For n equals 1, this goes again back to the cavity. And for 2n minus 1 is the number of singularities in the denominator. N is the number of charges in the numerator. For n equals 1, this goes back to the cavity I just discussed. For n equals 2 or larger, this can be understood geometrically in terms of elliptic or hyperelliptic curves. But really, these are quite explicit expressions. And for n equals 2, the elliptic case, you can actually give explicit expressions for the holomorphic functions in there in terms of incomplete elliptic integrals. So this is something which is very tangible. These are things you can feed into Mathematica, plot and play with, and corresponds in the earlier discussions to a single charge disk, but not in the limit where I send it off far away. I'll keep it at finite distance. So this is a very explicit realization of these solutions. To sort of hammer this home, you can, like I said, you can feed this into Mathematica and make plots. You see here the metric on the Riemann surface. The radius of the 6-sphere collapses on some boundary segments. Radius of the 2-sphere collapses on other boundary segments. We have the full set of potentials. This is something to play with. OK, the last point I want to make is that sort of this recovers the solutions that have been there before. But this sort of systematic classification type of approach gives also additional ingredients. And those are these poles with PQ string charge and PQ 5-brane charge. Now, you may wonder, maybe they never appear in regular solutions and are just not part of the discussion. I found them in this classification, but can they be part of regular solutions? And the answer is yes, they can. The simplest example is you take one segment with S2 collapsing, one segment with S6 collapsing. You can add a pole in here, and there are regular solutions of this form, where at this pole you have an asymptotic region emerging, which again has this asymptotics with positive string coupling, but the axion diverging. We've seen this a few times by now. And actually, this particular simple solution can be seen as a deformation of the cavity that I mentioned, where the dilaton is negative. You basically move this pole towards this transition point. You have 1 over w squared merging with the square root singularity to give you w to the 5/2. And this connects it back to the cavity. It would be interesting to sort of see how this kind of ingredients tie into the other regular solutions that I discussed. For now, this is kind of a classification type of approach. This is certainly a playground to be explored and see if this can perhaps regularize some of the discussions that we've had in the connection with IKKT. Good. So let me conclude. That was the last slide. So I tried to give you an overview of this classification of the complex F4 solutions in complexified type 2B with all of its real forms, because we can. We have a sort of toolbox for global solutions that were previously connected to the IKKT model, which have a natural action of SL2R. We classified some new ingredients, and it would be it's sort of the plan for the future then is to use these explicit solutions for detailed tests of these IKKT holography proposals. This was already mentioned in one of the questions. What you want to do now is take these solutions and poke them, add some probranes to it, let's say, match them to excitations in the IKKT model, things like that. This is work which is currently underway with a postdoc and a master student in Brussels. One can also imagine adding further ingredients to the solutions. So far, we took them to be single-valued, so no 7-brane monodromies. But this is something we can really attack now that we have this natural SL2R action that's there to be done. More broadly, this is sort of one side of the story for a general connection between the complexified IKKT model and complexified type 2B string theory. It would be interesting to discuss to study, for example, the real forms with de Sitter factors and how they may connect to the Lorentzian version of the polarized IKKT model that comes with its own convergence issues and things like that. But anyway, to get to something like a fuzzy de Sitter space would be interesting. And then there's the whole question of negative branes and supergroup gauge theories connecting to 5D CFTs. So there's a lot to do, but that's it for now. Thank you very much.
So this is officially our first discussion. So the goal is to ask broadly. We have maybe 50 minutes to discuss. I don't know if you have something that you find particularly challenging or interesting that is worth making that point.
Yeah, so I think the main challenge is to, we're kind of used to doing ADS CFT, where a lot of these things are under pretty good control. Start from a brane construction, see what field theory this engineers, see what gravity solution you get from it. Then we have precise connections between these two. Here, this is really kind of open, more open territory. And extending things beyond the dictionaries that have been proposed would, of course, be the main punchline and goal here. More generally, of course, having some gravitational setups with time emerging from some underlying degrees of freedom without time, that would be nice to understand. Of course, in some sense, yeah, maybe I'll leave it at that. Some notions of emergent time and emergent de Sitter spaces, which we seem to see here, that would be an exciting thing to make more sharp and precise.
So the reality conditions that you impose in the solutions of type 2b, you expect them to inform you about something about the emergent time or emergent space-time in the IKKT model. Do you have any kind of inference about how they would transfer over?
Yeah, so in some sense, once you think, one way to think about it, I would say, is looking at IKKT as dimensional reduction of, say, n equals 4 super Young mills. You can go through this in a way which connects to real forms, signature 1,9. Basically, you start compactifying, dimensional reducing, including the time direction. And what that gives you is a theory where you have a non-compact R symmetry in some sense. And this is actually one of the ways, like if you look at the localization calculations that are being done, in those cases you want a Euclidean theory with compact R symmetry. So that usually means, well, you think of a Lorentzian field theory, analytically continue it. But you could, for example, do things like construct a Euclidean n equals 4 super Young mills by starting in 10D with n equals 1 super Young mills, reducing on T1, 5. That gives you a Euclidean n equals 4 super Young mills theory, where the R symmetry is SO1, 5. And this theory naturally lives on Euclidean D3 branes. So that lives in type 2b star already. This is how Peston constructed the theory for the localization calculations. And then the second step, you choose a contour for the R symmetry where you compactify it. So it's this, in some sense, Lorentzian IKKT I would view as the 0 plus 0 dimensional version of that. Take this discussion and reduce it to 0 dimensions. So you end up in theories where you have de Sitter spaces, but they morally are related to something like R symmetries. And that's sort of one way to look at the way emergent time comes about here.
Hi. I think you mentioned that the IKKT model can be obtained as a reduction of n equal 4 super mills. Is it correct?
Sorry.
So you mentioned that the IKKT model can be obtained as a reduction of n equal 4 super mills. Is it correct? I mean, the reduction is on what space, S4 or what?
It's just sort of the same way you think of reducing from 10D n equals 1 to n equals 4 super Young mills. You put it on torus, nobody gets to depend. And that gets you from 10D to 4D. And now you can do this basically with tori of different signatures.
So it's a trivial reduction on flat space. There is no S4 involved.
Yeah.
Okay, I was just wondering if you can make the S9 appear at the boundary as an S5 bundle over S4, which is possibly the case. But so if there is no,
I don't
S4.
think that's sort of the spirit here. It's really sort of the more trivial flat space, flat reductions. You do get the sense where, this is something which would, okay, maybe we go back to the real forms here to sort of comment a little more on that. So you see that the real forms here are DS1,5, the ones which have time in here. We have a 6D de Sitter space in type 2B star. We have a 2D de Sitter space in type 2B star. If you look at the polarized IKKT model, what we did there was pick out a triplet of matrices. And now one can wonder, okay, can I do these polarization deformations in Euclidean signature, in Lorentzian signature, in the Lorentzian IKKT model? So here this was done in the Euclidean model, where I break, basically I retain SO7 and SO3. If I wick rotate and make this an SO1,6, it's naturally the symmetry group of 6-dimensional de Sitter space. It does do nothing to the polarization, but you could imagine doing a time-like polarization deformation to get the other real form. So those are the kind of connections that there are hints in these tables and results. But yeah, that's slightly different, I think, from what you're asking there.
Okay, and a related question, is there a way to obtain the polarized IKKT model from n equal 4 supermills by turning on some background field?
Okay, so I should separate. When I was talking about these dimensional reductions, what I meant is sort of the undeformed models. How this fits in with the deformed versions, that's a separate thing.
So that's unclear? That's not known?
I would, let's say, I don't have something sharp to say about this right now. That doesn't mean it's not known.
Okay, thank you.
I just wanted to know, can you elaborate a bit more on why there's not a well-defined large n limit for the IKKT model?
Yeah, you can basically, the undeformed IKKT model, that has been evaluated. It's a matrix integral, and it depends on some divisor function, which depends on really divisors of n, and that doesn't scale smoothly in the large n limit.
And like also, what are some tests that you have tried to see this holographic duality? As you mentioned, like inserting some probe brains, or like what are some things that you have been looking at, and what are the problems that you face?
So I'm not sure I caught but sort of have we looked at probe brains? Well, this is sort of in progress. You can so this IKKT matrix integral can be the polarized one, can be attacked using supersymmetric localization. It allows you to calculate not only the integral itself, but also all sorts of insertions into the integral. And that is something you can do and approach. And then ask, I add a little pokey thing into the matrix integral that should correspond to a small deformation of the gravity dual. So if it's sort of sufficiently benign introduction, it should correspond to probe brains, the gravity duals. And so one thing which is natural to do is to take these disk solutions, or in the language I was advertising, like let's say these kinds of solutions where you have alternating boundary segments with S6 and S2 collapsing. This is sort of these disk solutions. You can now ask, what additional probe objects can I put into these solutions? And can I somehow find a match between what I can put preserving a given amount of symmetry and what I can do in IKKT and connect results there.
Thank you.
So I just wanted to follow up on David's line of inquiry. So another way of looking at the n equal 4 super Young mills, as you said, is just n equal 1 standard super Young mills in 10 dimensions is one that we know sort of really well, except just reduce it to completely, make it depend on nothing, making it a matrix model. But then in that language, there's a deformation, as you say, right? There's this polarization. What does that correspond to in the level of 10D, this omega? What is it for a 10D Young mills? What has been deformed? Because apparently it's been deformed without breaking supersymmetry, really, right? So what is this? I mean,
It's a good question.
Because I mean, this is an established deformation now, right? And it's the only one that's consistent, basically, with the basic
this is
classifications of super algebras from the 70s or something. So it's okay. So it's something that you should be able to do in n equal 1 10D super Young mills, and saying what deformation is it, and that might give an idea about or a different perspective on the same things that other people, the brain configurations people were taking.
Yeah, that's a good point. I would say the closest analogy for this polarization deformation, which has been discussed and established, is basically it goes back to this paper which I had somewhere from 2002 by Bonelli. Basically it's a version of the BMN deformation of BFSS.
Right.
So that's a close connection which has been put to great use and utility. One can, spitballing. I mean, okay, we know what the.
But BMN is already on the supergravity side, right? It's a massive deformation of the supergravity. I'm just asking an algebraic question in quantum field theory.
Yeah, you can add a similar deformation to BFSS.
Oh, right, of course, BFSS. Yeah.
So that's basically where the closest connection is.
BFSS with no time. Yes.
Yeah.
So I think about the previous question, if you try to ask that what's the corresponding deformation from BFSS to BMN in the super Yang-Mills case, I think that corresponds to you put angles 4 super Yang-Mills on 3 sphere instead of T3. And then if you compare the dimension reduced on 3 sphere, you get BMN. So I would imagine similar thing might happen here. You can probably put angles 4 super Yang-Mills on probably S3 times S1 or S4, you can probably get a polarized IKKT, but I'm not sure.
All right, so let's thank Christoph again.